Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at the question 24 of the NAHPI 2021 entrance examination question. And the question 24 reads, two identical conducting spheres A and B carry equal charge. They are initially separated by a distance much larger than their diameters, and the force between them is F. A third identical conducting sphere C is uncharged. Sphere C is first touched to A, then to B, and then removed. As a result, the force between A and B is equal to, so this is the question they're asking you. So that's why I'm putting a question mark there. So you're given options A, B, C, and D as always. But the challenge is always to determine which of these options is correct. For you to be able to do that, you need to read your question again and you bring out the important information. Every single piece of information that you find important should be noted and even underlined. Okay, they said two identical conducting spheres. The first thing to take note of is that there are two identical conducting spheres. The spheres are spheres A and B, and they carry equal charge. So if the charge is Q, then the charge of A, Q of A must be equals to Q of B. That is, the charge on sphere A must be equal to the charge on sphere B. They are initially separated by a distance much larger than their diameters. We take note of these two. And the force between them is F. So it's obviously the electrostatic force of repulsion. Since the spheres are identical, they obviously have the same charge, the same everything. And so since they are identical, there is a force of repulsion between them, and that force is F. A third identical conducting sphere C is uncharged. So good. They have told you that there is a third sphere, a conducting sphere too, and it is uncharged. Therefore, the net charge on sphere C, Q is 0. Let's say Q of C, charge on C is equal to 0. That is what it means for the sphere to be uncharged. That is, the amount of positive charge is equal to the amount of negative charge. So all the charges on the body neutralize. Sphere C is first touched to A, then to B, and then removed. So you first of all touch sphere C to A. This is a condition that is important to take note of. Sphere C is first touched to A and then to B. So when you touch it to A, you remove it, then you touch it to B, and you now remove it from B too. As a result, the force between A and B is equal to. So the very last thing you may want to ask yourself after reading this question is, what happens when sphere C is touched to sphere A? And then what happens when sphere C is also touched to sphere B? Remember that all the spheres are identical, but sphere C is uncharged. And the first thing you did was touch sphere C to sphere A. So effectively, this is the setup you have before sphere C was introduced. So there's a force of repulsion. The distance between them, which is much greater than their diameters, is R. So it is this distance, the distance in blue. And the two spheres are identical. As you can see, they have the same mass, the same size, the same radius, the same diameter, and everything. And most importantly, the charge on the two spheres is the same. So if this here is, let me call it Q. So I can see it is Q of A, and this here could be Q of B. Then you notice that Q of A, that is the charge on sphere A, is equal to the charge on sphere B, and that charge, this is B, the charge on sphere B, and it is equal to Q. So they all have the same charge. So, and is equal to Q. Alright, so the magnitude of the electrostatic force of repulsion between sphere A and sphere B is given by F equals KQ squared on R squared, where K is a constant which is equals to 1 on 4 pi epsilon 0. When sphere C is touched to sphere A, the final charge on both spheres becomes Q on 2, since charge is a scalar quantity. So the net charge is equal to Q plus 0 on 2. How do you get this? Okay, this is your uncharged sphere C. So this is your sphere C, and this is your sphere A. So actually you are going to make sure that sphere C touches sphere A. So initially we had 1, 2, 3, 4, 5, 6 charges on sphere A. So when the two conducting spheres touch each other, there is charge redistribution. The charge redistributes such that the charge on A becomes equal to the charge on C. Effectively, you are going to obtain 1, 2, 3 positive charges on the sphere C, and for the sphere A, you also be left with 1, 2, 3 positive charges. And if you separate the two spheres, then you are going to have your sphere C and your sphere A. Your sphere C will be left with 1, 2, 3 positive charges, and the sphere A will also be left with 1, 2, and 3 positive charges. Then effectively, if the initial charge on A was Q, then after charge redistribution, the charge on sphere C becomes Q on 2, and the charge on sphere A becomes Q on 2. And even when you separate them, the charge on sphere C becomes Q on 2, and the charge on sphere A becomes Q on 2. So taking 6 positive charges here and showing you the process of charge redistribution is just an example. It doesn't actually mean that there are 6 charges on sphere A. So that is why, to get the net charge, you simply take the charge on sphere A, that is QA, plus the charge on sphere C divided by 2. Since the sphere C was uncharged initially, then we are left with QA on 2. Since QC is equal to 0, and since QA is equal to Q, then we have Q on 2. That is the net charge on sphere C and sphere A. So now when sphere C is taken away from A and then touched with B, the net charge becomes, so if this is now your sphere C, remember your sphere C has a charge Q on 2. This is your sphere C. And this is your sphere B, having the same charge initially as sphere A. So when you touch the two, so let's say this is our sphere B. When you touch the two spheres, C and B, Q on 2 and Q. So when the two are made to touch each other, charge redistribution occurs such that the net charge becomes charge on sphere C plus charge on sphere B divided by 2. Effectively, this is going to give us 3Q on 2 divided by 2, which gives us this answer. So for you to be able to get the net charge on each of the spheres, you simply sum the individual charges and then you divide it by 2. Since the charge redistributes itself such that the charge on each of the spheres will be exactly the same. So you just have the sum of their charges. Okay, now the force between A and B after C has been removed becomes, remember after C has been removed, sphere A is left with a charge Q on 2 and sphere B is left with a charge 3Q on 4. So when you replace the quantities in your formula, you are going to obtain, this is the charge of sphere A, this is the charge on sphere B. When you do that, you are going to obtain 3 on 8Q squared on R squared. But remember that KQ squared on R squared is equal to F. Effectively, you are going to obtain F prime to be equal to F.